Okay. First of all, I want you to remember what a horizontal asymptote is. On Friday, we talked about vertical asymptotes. Today, horizontal asymptotes will be important for what we look at. Okay. So horizontal asymptotes describe the ending behaviors of our graph. Basically, what's happening towards infinity, what's happening towards negative infinity. If you remember back in Algebra 2 and pre-calculus, it is okay for a function to cross the horizontal asymptote as long as by the infinities it approaches the horizontal asymptote. You guys remember some of those graphs that cross through? Okay, so why am I reminding you about horizontal asymptotes? Today we are going to look at limits towards infinity. So Friday we looked at limits of infinity. When we were approaching our vertical asymptotes, our limits were either positive or negative infinity. Today we're going to look at limits as x approaches infinity or limits as x approaches negative infinity. Okay. An infinite or a limit towards infinity is basically asking you what is the ending behavior of the graph. Okay, and this is how we write them. The limit as x approaches negative infinity, the limit as x approaches positive infinity. What is happening at the end of our graph? Okay. When there's a horizontal asymptote, it's going to approach the horizontal asymptote. Now, not all of our graphs have horizontal asymptotes, right? No. So we're going to talk about a few different types of functions and how we determine what's happening towards infinity or positive infinity. Most of these rules you already know. We're just going to apply them to finding limits, okay? Here again, a lot of your work is going to be thinking analytically about what's happening with our graph. You're not going to be writing a lot of work, okay, but we need to be thinking about certain things. So the first family of functions I want to talk about are polynomials. We talked about both in Algebra 2 and in pre-calculus something called the leading coefficient test to figure out what's happening on the right and left-hand sides of our graph. So I want you and your pod to take about 60 seconds and try to come up with the rules for the leading coefficient test. How do we know if the right is going to rise or fall? How do we know if the left is going to rise or fall? 1, 2, 3, go. Okay, let's come out together. Pod 2, give me one of the rules you talked about. Okay, what about the rest of your group? Did they remember anything? Okay, maybe Pod 3 can help us out.
Well, if you have a leading coefficient or exponent, it's gonna both of them are gonna be the same thing. So if it's negative, they both fall, and if it's positive, they both rise.
Even degree, you're saying right and left are going to have the same behavior? Right, that's what you said? Mm-hmm. Which means if we have an odd degree function, right and left are going to go opposite ways. Okay, pod 4, how do we know if the right side or left side is going to rise or fall?
If the coefficient before the first x with the highest degree is negative or positive.
Okay, so if we have a positive leading coefficient, what does that mean?
Well, for even degrees would go both are positive.
Okay, what about for odd degree? How do you know which one's going to rise?
You would know that the right side is going to rise.
Okay, so if we have a positive leading coefficient, the right side is going to rise. Negative leading coefficient, the right side is going to fall. Even degree means they're both the same. Odd degree means they're opposite. So you first look at the leading coefficient, and that tells you what's happening on the right side of your graph. Then you look at the degree, and you can determine what's happening on the left side of your graph. Is it the same or is it opposite? Okay. If I give you limits towards infinity of polynomials, you need to think of the leading coefficient test. Okay? Now that we've talked about this, does this ring a bell? Yes. Okay. So, we're going to go through some examples. We'll start here. I have the limit as x approaches positive infinity of 2x to the fifth. And I have the limit as x approaches negative infinity of 2x to the fifth. Okay. Larry, what's happening on the right side of our graph? Is it rising or falling?
Rising.
Rising because? Okay, so towards infinity, we are rising indefinitely, right? Towards the left side of our graph, Logan, what's happening on the left side? We're going to be falling because we have an odd degree, so we have to have opposite behaviors. We're going to continuously fall, so we're going to go towards negative infinity. Do you remember last year how you wrote, like, as x goes to infinity, f of x goes to infinity? You remember writing that? You basically were doing limits last year, you just didn't know what they were. Okay. Next example, the limit as x approaches positive infinity of 5x to the sixth, and the limit as x approaches negative infinity of 5x to the sixth. Okay. Aaron, what's happening towards the right side of our graph? We're rising, so we're going to positive infinity. Cole, what about the left side?
You're right.
You're also rising. Okay. Negative 7x to the fourth. Okay. When you see positive infinity, we're thinking about what's happening on the right. When you see negative infinity, we're thinking about what's happening on the left. Okay? So Gina, what's happening on the right side of our graph?
Falling.
It's falling. So our limit's going to be negative infinity. How about on the left side of our graph? Jennifer, what's going to be happening?
It's falling.
Also falling. We have an even degree. All right, I'm going to put two limits up here. I want you and your pod to come up with solutions. So I want you to work together to come up with common solutions for these two. Okay, pod 1. How about this first one? positive infinity. Do you agree with pod 1? Okay, our leading coefficient is indeed positive. Okay, pod 6, how do you feel about the second one? What'd you get?
Well, we're in a disagreement.
Okay.
It was falling.
Okay, so you're saying negative infinity, but who's disagreeing?
We're in agreement now.
We're in agreement
We
now.
made it CR.
Okay, so can you explain to the rest of us?
Yeah, so at first we were looking at the 17, and then we're like, no, we should probably look at the one with the highest exponent. So then we moved to the negative 14, and because it's negative, that means the point.
Okay, I tried to trick you.
Okay.
Not always are polynomials going to be written in order. I like polynomials written in order, but sometimes they could be mixed up just to make sure you're paying attention. The leading coefficient technically is negative 14 because it is with the x of the highest degree. So the left side is falling because the right side is also falling because we have an even degree function. Okay? All right. A rule. The limit as x approaches infinity of something over a polynomial is 0. Or the limit as x approaches negative infinity of something over a polynomial is 0. I'll let you write it down. And then we'll talk about why that's true. This is the example that we're going to talk about with it, okay? Basically, if we have x to a power, x squared, x to the 4th, x to the 16th, okay? As you go towards infinity, that means that denominator of x squared, x cubed, x to whatever power is going to go either to infinity or positive infinity. What's going to happen if you take a number divided by something that's really, 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 really big? What are your numbers going to approach? 0, right? The bigger your denominator gets, the smaller your fraction will be, okay? So if our denominator is approaching infinity, that means our fraction is going to be approaching 0, okay? So here I have the limit as x approaches infinity of 5 minus 2 over x squared. What's the limit as x approaches infinity of 5? Say it louder. 5 minus, what's the limit as x approaches infinity of 2 over x squared? Okay, 2 over infinity is kind of how we can think about that. That's going to go to 0. So we're left with 5. Okay. We're going to use this to help us evaluate more complicated limits. All right. So here is where the work begins, okay? So far, we really haven't had to show any work. We've really just kind of thought about things, right? And there'll be a little bit more of that. But I'm going to start by showing you how to do this one. We're gonna do it one way, and then I'm gonna show you how to do it a second way, and you can decide which one you like better. Okay? If we think about like direct substitution, okay, or not necessarily direct substitution, if we look at this as a limit of a function divided by a function, if we think about the limit as x approaches infinity of our numerator, we know that that's infinity. If we think about the limit as x approaches infinity of x plus 1, that's also infinity. Okay? This is another one of those indeterminate forms. That is not 1. Okay, we cannot call that 1. We can't really do infinity over infinity. Okay? But one strategy that we can use is we can divide everything, every term, by whatever is the highest degree in the denominator. Okay? We can take every single term in that fraction and divide it by the highest degree in the denominator. So, what's the highest degree x in the denominator? X to the first. So what I mean by this is we can take everything and divide it by x. So I just took every term, since x to the first was our highest degree, I took everything and divided it by x. Now let's simplify this down a little bit. 2x divided by x is 2 minus 1 over x. And x over x is 1 plus 1 over x. Okay? Now we have something familiar. The limit as x goes to infinity of 1 over x. What did we talk about that? That's going to be 0. The limit as x approaches infinity of 1 over x. That's another one of our rules, 0. So we have 2 minus 0 over 1 minus 0, which is 2. Did a lot of work there. First of all, are there any questions about the work that we just did? Is there an easier way? What is it, Austin?
Just separate the two terms in the beginning, having 2x over x plus 1, and then minus 1 over x plus 1. And then you know that on the 2x over x one side, you're going to have infinity on the bottom, and then 2 times infinity on the top. And then the other one's going to just go straight to 0 because it's going to be 1 over x plus 1, so it's going to be 2 minus 0. And then equals 2.
Okay. I like where you're trying to go with that, Austin, but you still said infinity over infinity, and we can't think about that as canceling out. Infinity is not a number, so they can't just like cancel out to be 2. Okay? I want you to think about the graph. What kind of graph is that? What's happening at x equals negative 1? There's a vertical asymptote. Most of the time, I say most, not all, most of the time, if there's a vertical asymptote, we could also have a horizontal asymptote, which is at 2. Okay, Cole, so how do we know way back up here that our horizontal asymptote is at 2?
Well, since they have the same degree as an exponent, you can put the leading coefficients over each other.
Okay. Here's the deal. If we have a rational function and we know that it's going to have a horizontal asymptote, we know that our ending behavior has to approach that horizontal asymptote. Remember that first picture that I showed you? If we have a horizontal asymptote towards infinity and towards negative infinity, it's going to approach that. So instead of doing all this work, you can if you want to. But if you want to remember your asymptote rules, you wouldn't have to do any algebra. You could just think of where the asymptote is and identify the limit. Okay? So Cole already mentioned If the degrees are the same, then we look at the leading coefficient, and that's where our horizontal asymptote is. What is true if the denominator has a bigger degree? It is 0. Okay? If the denominator has a bigger degree, it will be 0. We'll go through examples of each of these three. What about if the denominator or the numerator has a bigger degree? Well, there is no horizontal asymptote, but potentially what kind of asymptote could there be? A slant asymptote. Just not do those at all?
Yeah.
Okay. All right. So 3 examples, one of each kind. Okay. Here, we have the limit as x approaches infinity of 3x plus 5 over 6x minus 5. Let me remind you that these horizontal asymptote rules only work if you're looking at limits towards infinity or positive or negative infinity. Okay, it's the only time these are going to work because horizontal asymptotes give us end behavior. Okay, so our degrees are the same, which means we look at, what do we look at, Josh? Okay, we're actually going to look at the numerator, leading coefficient, and the denominator. So our leading coefficients are 3 over 6, which means our horizontal asymptote is where? Say louder, Larry. 1/2. So our limit towards infinity is 1/2 because that's where our horizontal asymptote is. We only look at vertical asymptotes if we are evaluating the limit where the vertical asymptote is. Okay? And on that note, Cole, we only look at the horizontal asymptote if we're evaluating the limit towards infinity or positive infinity. Okay? So now all these rules, they seem very simple when we're working on them separately, but tomorrow, when I give you your review, you're going to have to separate out when do I need to use which rule. Okay? Okay, I'm actually going to come down to this one first. The limit as x approaches infinity of 3x minus 5 plus 2x cubed over x to the 4th minus 5x plus 2. What's true about the degrees? Are they the same or is one bigger? The denominator's bigger. Which means what's happening with our horizontal asymptote? Where is it? It's at 0. So since our horizontal asymptote is at 0, this is going to go to 0. Another way for you to look at this is the denominator is going to get bigger faster than the numerator is. So our denominator is getting bigger and bigger and bigger and bigger, which means their fractions are getting smaller and smaller and smaller and smaller. We're approaching 0. Okay, now this middle one is an example of a slant asymptote. Okay, the numerator is bigger than the denominator. I will tell you when we have a slant asymptote, and you can think about the picture. If we have a slant asymptote, so vertical slant. As we go to infinity or negative infinity, your slant asymptotes will also create that unbounded behavior towards infinity or negative infinity. So we just need to figure out, is this going to go towards positive or negative infinity? Okay? Identifying that there is a slant asymptote isn't really going to tell you the answer. You're going to have to do the way that I taught you. Okay? So what is the highest degree in our denominator? Okay, So we are going to have to divide everything by x to the first. So what we have is 2x minus 4 over x divided by 1 plus 5 over x. As we go towards negative infinity, what's happening to 4 over x? That goes to 0. What's happening to 5 over x? Okay. So what we are left with is the limit as x approaches negative infinity of 2x. What's happening to the left of 2x? Are we falling or rising? We are falling. It's a line with positive slopes. The left are going to be falling. Okay? So when there's a slant asymptote, you're going to have to divide each term by that highest degree of the denominator. There's really no getting around it. Okay, two more examples that are very similar. Okay? So far, we've talked about polynomials. Think about the leading coefficient test. Then we've been talking about rationals. Let's think about horizontal asymptotes. Now, I have a rational for you, except there is a radical in the denominator, and that's going to change things. Okay, so go ahead and write this one down. Technically, what's our highest degree in the denominator? It'd just be 1, right? We have x squared under the square root, so our biggest degree is x to the first. Does that make sense? Okay, so what we are going to do to evaluate this limit is divide everything by x. Now, when we're under the radical, x is the same thing as the square root of x squared. So when we're under the radical, we have the square root of x squared. Now, we do not have to make any adjustments because if x is positive, the square root of x squared is positive, this substitution is fine. Okay? So what we have is 3 minus 2 over x divided by the radical 2 minus 1 plus 1 over x squared. Okay? We do this, so this will happen. We have the limit as x approaches infinity of 2 over x. 0. 1 over x squared goes to 0. And we're left with 3 over radical 2. Did anybody think that was going to be our answer? Did they identify that? Okay. Where we have to be careful with this, okay, like I mentioned before, square root of x squared is x as long as x is positive. If we approach negative infinity, okay, same function, now our limit is negative infinity. Okay, we have to be careful with this radical. here again, our highest degree is technically x to the first, because we have the square root of x squared. So we will, like we did earlier, oops, this is negative infinity. We will divide everything by x. And under the radical, we'll divide everything by x squared. Here's where we have to be careful. If x is negative, what happens when we take the square root of x squared? What kind of number are we going to get? If we square x and then take the square root, what kind of number are we going to get? We're going to get a positive number. If we take a number squared and we square root it, it will be positive, right? But what if we're going towards negative infinity? What's true about all of our x's? They are negative, right? We're going towards negative infinity, our x's are negative. So if our x's are negative, to get this to equal, we're going to have to throw a negative on the square root of x squared. Since x is a negative number, the square root of x squared also needs to be a negative number if we're going to do this. So since x squared with the square root is positive, we are going to have to adjust our limit by throwing a negative out there so that we don't change the value. Okay. So then what's going to happen? We have 3 minus 2 over x over, we have that negative outside, 2 plus 1 over x squared. Just like before, these go to 0, and now the limit towards negative infinity is 3 over negative radical 2. Okay. What's happening with this graph is that there's 2 horizontal asymptotes. Let's see if I can get my calculator to pop up here. Help me out. What was the function?
X minus 2. Over radical 2x squared plus 1.
Minus 1.
Plus
Okay. So what's happening is there's 2 horizontal asymptotes. Towards infinity, we're approaching that 3 over radical 2. But towards negative infinity, we're approaching the negative 3 over radical 2. Okay. So we have to do that adjustment so we can figure out which asymptote we are looking at. Okay. So if you have a square root in your rational function, when we're looking at negative infinity, you're going to have to remember to make this negative adjustment so you can get to the correct answer. Okay. All right, this is your last set of book work for like a week and a half. It's rough, I know. Make sure you go through this book work. Tomorrow we'll obviously answer questions about it. We're going to do an activity. You'll get a review for your quiz on Thursday, and then review for a test. So, last set of book work for a while. Cole, did you have a question?